In this short lecture, I want to focus on a certain type of op-amp circuit, mainly a filter. And I want to start out with the inverting amplifier topology, where you have R2 and R1 and a grounded non-inverting input, and we have a voltage source VI and the output voltage VO, and we know that this Vout is equal to minus R2 over R1 times VI. I want to expand this to a more general topology, where instead of using R1 and R2, I'm going to use Z1 and Z2. So this circuit looks much like the first one, except we have two boxes, Z1 and Z2, instead of R1 and R2. If you solve this by writing KVL or KCL at the inverting input, you're going to end up with the same expression as the case where we have R1 and R2. Mainly, Vout is equal to minus Z2 over Z1 times VI. The special case would be if Z2 is equal to R2 and Z1 is equal to R1, then of course the output voltage is just minus R2 over R1 times VI. But now suppose that we replace R2 with a capacitor, C. Then what would we have? Well, we could immediately write as Vout is equal to Z2 minus Z2 over Z1 VI, but then we'd want to replace Z2 with the impedance of the capacitor, which is 1 over SC, and the impedance of the resistor, which is just R1. And so we have 1 over SR1C times, oops, that's supposed to be VI, VI times VI. Okay? And what this tells us is essentially that, let me rewrite it one more time. VO is minus 1 over R1C times 1 over S VI. Now you know by now that a 1 over S is really an integration operation, just like S times VI would be the derivative of VI. Right? If you recall, if VI is of the form, say some constant e to the st, then the derivative of VI is going to be S times k e to the st, or S times VI, right? And the integral of VI is going to be 1 over S k times e to the st, in other words, 1 over S times VI. So one of your homework problems, actually, I think two of your homework problems, involve a case where Z2 or Z1 are capacitors, and you're asked to show that the output is equal to the derivative or the integral or something like that. And you can solve that by actually in the time domain, like so. For instance, we can say KCL here at V minus would be VI over R1 plus VO. Well, let's see what we have. We'd have the current flowing here, IC, is equal to C dV, if we define this as VC, C d VC dt, which is going to be C dVO dt, because V minus is equal to V plus is equal to 0. So we could write C dVO dt is equal to 0. And from that, we can write that dVO is equal to 1 over R1C V1 dt or VO is equal to 1 over R1C integral of VI dt. Okay, so we can do it from the time domain as well. And in that homework problem, you can do it from the time domain, you can do it in the frequency domain with S as well. I want to rewrite this expression for VO as by using the variable or the letter H for transfer function, H of S VI. Okay, so we have VO is equal to H of S times VI. Now, using this, let's consider something else here. What if I had an R1 here, and instead of just a capacitor, what if I had an R2 and a capacitor? And I said, find VO. Well, you could write VO is equal to H of S times VI, where H of S is always minus Z2 over Z1, and in this case Z2 is R2 plus 1 over SC divided by R1. And we can clean this up a bit by multiplying through by SC, so we'll have minus SR2C plus 1 over SR1C. Okay, and we can even rewrite that as, let's see, S over some 0 divided by S, the whole thing divided by R1C, where omega Z we would say is 1 over R2C. So this goes back to when we were doing the sinusoidal steady-state response, and we were saying, okay, let's excite some system with an input VI that's sinusoidal, cosine omega t. What is the steady-state response V out? And we found that all we had to do was to find the magnitude and the angle of H of the transfer function evaluated at the frequency that we were exciting the system at. And here you can do the same thing. Let's take one other example here. What if I had, this can get messy pretty quickly, but just to show you how relatively easy it can be to solve these transfer functions, these op-amp transfer functions, simply by knowing the inverting amplifier architecture, which gain statement, which is minus Z2 over Z1. I'll have C2, C1, and R3. Okay, so now we could write, all right, it's H of S times VI, where H of S is equal to, okay, Z2 is R2 plus 1 over SC2 divided by R3 in parallel with R1 plus 1 over SC1. And we can work with this a bit. Let's see, we're going to write R3 R1 plus R3 over SC1, whole thing divided by the sum of the resistances, which impedances, I'm going to put that up on top. It'll be R3 plus R1 plus 1 over SC1. And if we multiply through by SC1 C2, okay, so we'll multiply through by SC1 C2, top and bottom, S squared. Let's do S squared C1 C2. Then we'll have R2 C2 S plus 1 times R1 plus R2, or R1 plus R3 times C1S plus 1 divided by let's see, SC2 times R1, R3, C3S plus R3. Is that right? Yeah, so we could write this out one more time as S over omega Z2 plus 1 times S over omega Z3 plus 1 divided by, and then this I can pull out the R3, so we'll have R3 C2S times S over omega P plus 1, where omega Z2 is going to be equal to 1 over R2 C2, omega Z3 is equal to 1 over R1 plus R3 C1, and omega P, pole, is going to be 1 over R1 C1. So what I'm pointing out here is that you can readily write the transfer function and therefore the output voltage of an op-amp filter as a function of the input by simply harnessing the VI-VO relationship of an inverting op-amp as being minus Z2 over Z1, and then substituting Z2 and Z1 with the appropriate combined impedances. And although it's a lot of algebra, you can put it into a standard form here, and we see that for this particular filter we have a transfer function that has two zeros, two finite zeros, and two finite poles. The one pole is going to be at S equals 0, and then the other one is going to be at omega P. Alright, let's do an example of an op-amp having a certain transfer function. We'll use an inverting architecture. Suppose we have this topology right here. So what I want actually is I want an amplifier that has a gain of 10. So here's what I'm looking for actually. If I were to plot frequency, I would like for the transfer function VO over VI, okay, the magnitude of that, I'd like it to have a gain of 10 up to a certain frequency, and then I want it to basically filter out the higher frequency. So I want it to go down like this, and so that, let's see, maybe by, let's say I haven't picked values here, so okay, let's just see what happens here. I know that I have R1 here. I'm going to call that 1. I'll give that a value of 1K, and I'm going to have R2. I'm going to give that a value of 10K, because R2 over R1 is going to give me my gain of 10 that I'm looking for. And let's see, I've got to pick my value of capacitance. I would like this knee right here to occur at 1,000 radians per second. Okay, so let me pick a value for that. That means I need to have 10 to the 4. I think I need this to be 100 nanofarad. We'll see if that works out. Alright, so then the question is, if VI equals cosine omega t, find VO steady state. This is going to be where omega is equal to 1 radian per second. We'll do 1,000 radian per second, and we'll do, say, 10,000 radian per second. Okay, so we already know VO is equal to H of S times VI, where H of S is going to be minus Z2 over Z1. Right, now in this case, Z2, this is Z2. So we have minus 1 over SC in parallel with R2 divided by Z1, which is just R1. So we'll have 1 over SC times R2 divided by, I'll just put it down below here, divided by 1 over SC plus R2. Let's multiply through by SC. So we'll have R2 minus R2 over R1 times 1 over 1 plus SR2C. And I'll write this one last time in a standard form. We'll have minus R2 over R1, 1 over 1 plus S over omega P being the pole, and it's equal to 1 over R2C. And for R2 and C values, we have 10 to the 4 times 10 to the minus 8. Oh, I messed this by 1. I wanted to have 10 to the minus 7. So I want this to be, 100 nano is 10 to the minus 7. That's right. That's right. Okay, so that ends up being 10 to the minus 3, or omega P is 1,000 radians per second. Okay. So let's just consider if VI is equal to just 1 volt. Okay, this means S is equal to 0, right? Because it's a constant. Then VO is equal to H of 0 times VI, which is 1 volt. So I get minus R2 over R1 times 1 over 1 plus 0 over omega P times 1 volt. And so we end up with minus R2 over R1 times 1 volt, which is equal to minus 10 volts. And we do end up getting our gain of 10. Now, I'd asked for a gain of 10, a magnitude of 10. In this case, we have a minus sign along with it. But our magnitude is 10. So at DC, if you put in a DC value, you're going to get a gain of minus 10. What is it if VI is equal to cosine of 1 times T? Well, VO is going to be equal to the magnitude of J times 1, H of J1, times cosine of 1 times T, plus the angle of H evaluated at J1. So H of J1, magnitude, is going to be equal to minus 10, because that's minus R2 over R1, times 1 over, we have square root of 1 squared, plus, and here we have 1 over 1,000, right? 0.001 squared. All right, this is, the denominator here is going to be very, very close to 1. So I'm going to say this gain is approximately minus 10 still. The angle of the transfer function is going to be angle of the numerator, which is angle of minus 10, right, minus the angle of, what will it be, 1 plus 0.001J. Well, this is going to be approximately, it's going to be 180, right, minus 10 would be plus or minus 180, minus, and the angle for the denominator here is going to be approximately 0, right? Because 1 just swamps out the 0.001J. So we're approximately at minus 180 degrees. So we have VO is approximately minus 10 cosine 1 times t. Right. If VI is equal to cosine 1000 t, right, then we have the magnitude of h of j 1000 is now minus 10 times 1 over the square root of 1 squared plus, and in this case we have 1000, j 1000 over 1000. So we have j, it's basically 1, so 1 squared. So we're going to have minus 10 over the square root of 2, which is approximately minus 7.07. The angle of h of j 1000 is going to be equal to minus 180 as before, minus the angle of 1 plus j, which is minus 180 minus 45 degrees, which is minus 225. Okay, so the way we could write this, we could write it several ways, but we'll say V out is equal to minus 7.07. Wait, I can't have a minus sign up here for the magnitude. Sorry, there's no minus 10 there. But I'm going to put my minus 180, this part here, I'm going to put that with the minus sign here rather than, or capture that with the minus sign instead of capturing that with the phase in the cosine term. You can do it either way. Cosine of 1000 minus 45 degrees. Okay, and then finally, if VI is equal to cosine 10,000 times t, then the magnitude of h is going to be going to be 10 times 1 over, I realize up here I had an error in my magnitude. You can't have negative sign in your magnitude, so these were wrong right there. Okay, so 10 times 1 over the square root of 1 squared plus, and now this will be 10 squared, right? Because it's 10,000 over 1,000 squared. So now we're talking about something that's approximately 10 over 10, so approximately 1. And the angle of the transfer function is going to be equal to minus 180 minus the angle of 1 plus 10j. And that is equal to 5.7 minus 5.7 degrees. So we'd have VO is equal to minus 1. I'm going to put the 180 degrees, capture that in the sign again, cosine of 10,000 times t minus 5.7. Wait, no, I did that wrong. That is wrong. No, I did the arctan of 10 plus 1j, not 1 plus 10j. Let me recalculate that. That's 84.3 degrees. Okay, minus 84.3. Okay, so what's happening here? What we're finding is that as you increase the frequency above the 1,000 radians per second, that's the pole frequency, the amplitude of the output starts attenuating, and it attenuates essentially by an order of magnitude for every order of magnitude increase in frequency. So you notice that when we were at So when we were at 10,000 radians per second, in other words 10 times above the pole frequency of 1,000, we have an attenuation that's about a factor of 10. So we put in an input that is an amplitude of 1. The DC gain of the op-amp circuit is 10. So down at DC we would expect 10 volt amplitude out. By the time we get to 10,000 radians per second, we're down to a tenth of 10 volt amplitude. If we were to recalculate this at 100,000 radians per second, we would see that we'd be down to 1/100th of an amplitude of 10, so we'd be at 0.1. And at 1,000,000 radians per second, it would be 0.01 and so forth. And so we do have this attenuation here. If I were to, let me mark it this way on a log scale, okay? So this would be 10,000 radians per second. This point right here would be 100,000 radians per second. And at 1,000, what you have is, because it's right at the corner frequency, we end up getting 10, whatever the DC gain is, this is the R2 over R1, divided by square root of 2. And then at frequencies much lower than 1,000 radians per second, we have essentially a gain of 10. So what's the use of this? This would be very useful, a useful amplifier, if we have some sensor, could be a microphone, could be temperature sensor, where we really want to capture the, let's say it's a temperature sensor. I really want to capture the DC, or the steady, the DC temperature of the room. But I know there's noise in that temperature, or maybe that temperature fluctuates because doors open, doors close, and I don't want to respond to that. So I want to filter out those higher frequency fluctuations. So I could design this, or send the output of the temperature sensor through a filter like this. That on one hand gives me some low frequency gain, maybe that's something that I need, but on the other hand it'll actually then attenuate, remove that gain, in this case of 10, and even add attenuation beyond that for higher frequencies. Of course, if it was for a temperature in a room, you wouldn't want a corner frequency of 1,000 radians per second. Maybe you'd be talking about, a radians per minute or something, something very slow. So it would average over many seconds, maybe even over minutes. So there's an example of how you can use, how you can kind of merge or apply sinusoidal steady-state analysis to an op-amp filter circuit, where we have derived the transfer function of the op-amp filter by using one of the standard op-amp amplifier forms, specifically the inverting amplifier form, where we start out with minus Z2 over Z1 and proceed to write the transfer function from that impedance ratio.